IWCS webinar series event is hosted by the International Cable and Connectivity Symposium. I am Ed Fenton, a cable industry advisor working with the IWCS team. As Sammy said, if you have questions, please use the Q&A box on the bottom right of your screen to post a question anonymously. If you wish to contact the presenter or IWCS after the presentation, you will be given the contact points at the end of the webinar. Please note that IWCS does not distribute presentation slides from either our conference sessions or these webinars. However, please feel free to contact the presenter directly, and they will respond individually to you. Today, we welcome Peter Weimann, Technical Manager of the Cable R&D Group, OFS Fitel, LLC, in Carrollton, Georgia, USA, who will be presenting his paper on cabling and splicing performance of an ultra-low-loss, optimized effective area fiber for terrestrial long-haul applications. Peter Weimann is the Technical Manager of the Cable Research and Development Group at OFS Fitel in Carrollton, Georgia. His work during 18 years at OFS has included materials development for optical cables and design of optical cables for indoor and FTTX applications. He is a two-time co-recipient of the IWCS Fergal Award, as well as a two-time recipient of the IWCS Best Poster Paper Award. He holds a PhD in Material Science and Engineering from the University of Minnesota and BS degrees in Material Science and Organizational Management from the University of Pennsylvania. Pete, we welcome you today to present at today's IWCS webinar series event.
Okay, thank you, Ed. Thank you, Sammy, and thank you to the IWCS for giving me the opportunity to present on this topic. Good morning, good afternoon, and good evening to people listening in around the world. This paper was kind of unique for us in that we had an opportunity to work across multiple groups and divisions within the OFS family, people from our fiber division, people from our cable division, people from our customer support engineering operation, and people from our fusion splicer division to sort of talk about how we can carry a new optical fiber product from the drawing board out to the field. This is a slide that should be familiar to a lot of people who are on the call today. Data traffic on the public network, internet protocol traffic, continues to grow at a very, very fast pace worldwide. This data is taken from the Cisco Visual Networking Index. Cisco issues a forecast for how data traffic will continue to evolve in the future. And what's being forecast right now is a 22% compound annual growth rate through 2020. And video and mobile applications are growing faster than the rest of the market. So this is creating stress throughout the network, whether it's undersea, long haul, metro, or to the user. One particular area where we're seeing very strong growth in network demand is being driven by the cloud. As part of this growth in internet traffic, a lot of it's being driven by entertainment on demand, such as Netflix and YouTube, certainly two things that are very familiar in my house. We can have a situation where my wife and I are streaming Netflix live, and both kids are watching YouTube at the same time on computers or tablets. There's also applications that run in the cloud, like Microsoft 365 and Salesforce. These do not go on your computer. These come through an internet connection. There's also storage on demand, like Dropbox. And one thing that's going to rely heavily on the cloud is the emerging Internet of Things, whether it's transportation or smart cities or smart energy. A lot of those applications are going to be hosted and analyzed in the cloud. The cloud actually lives in data centers, either edge data centers or so-called hyperscale data centers. And service from these large data centers to users is growing faster than the overall growth in IP traffic worldwide. One part is the traffic from the data center to the user, projected to grow at 25% per year through 2019. And one part of that we're focusing on with this development is traffic between data centers. Often, data center service providers have to mirror content at different locations in order to serve content in different regions of the world, or also to back up content in geographically distinct locations. So traffic that's going just from one data center to another for this sort of thing is projected to grow at 31% through 2019. So far, the Longhaul Network, and here's just a plot, or here's some figures taken from the public internet from three very large cloud service providers, Google, Microsoft, and Amazon Web Services, Microsoft Azure. As you can see in North America, these are often geographically distributed. Google has a footprint all over the country. Microsoft has locations on both coasts, in Canada, in the South, and in the central U.S., and Amazon Web Services is localized on the two coasts. So in many cases, they'll have to get data from one data center to another data center across the continent. And similar trends are happening in other continents and other regions of the world. So far, long-haul networks that connect these remote data centers have been able to keep up with the demand, despite the huge growth in internet traffic. At this point in 2017, with standard ITU G652D fiber, with the right electronics, you can transmit up to 10 terabits per second on each fiber. With the development of dense wavelength division multiplexing, electronics are able to support 100 wavelengths in the C-band instead of just one. There's higher density modulation formats that have emerged, coherent detection, which takes advantage of different polarization multiplexing, which take advantage of different polarities to cram more data on the same fiber. And then with other developments in electronics, service providers have been able to achieve a 3,000-kilometer reach between regeneration sites, which will get you most of the way across North America. And that's through some forward error correction and new amplification formats. So with the same fiber that has been used in the marketplace for about 15, 20 years now, the long-haul networks have been able to keep up. But we're starting to see a change in that. Can these networks keep up with these new demands from the cloud? The plot shows reach without amplification against spectral efficiency. And where we are right now in the current marketplace is shown by the star. That's the 3,000-kilometer reach without regeneration over G652D fiber. But to go faster than the current standard of 100 gigabit per second per wavelength, to go to 200 gigabit per second, or to go to 150 gigabit per second or 200 gigabit per second, which will require higher order modulation formats, won't be able to achieve that 3,000-kilometer reach anymore. When we go up to 200G with the current modulation format for that, you can only get about 1,000 kilometers with regeneration. So if you want to use the existing base of fiber, that's going to require added signal regeneration sites. That requires putting huts out in remote areas, powering them, buying some fairly fancy electronics. That's going to add capital and operating expenditure for service providers. So what we're presenting today is a new ITU G654E fiber that can reduce the cost per bit of transmission and reach twice as far as G652D fiber in the same sort of transmission scenario. This fiber has a 49% larger effective area than the G652D fiber, as well as ultra-low loss. The larger effective area supports the ability to accept a stronger signal at higher launch power. So if you start with a lot more power, you can go a lot farther. The ultra-low loss supports longer transmission distances and lower noise. What we're really trying to do here is give service providers the opportunity to boost the optical signal-to-noise ratio, which is really the key to how far you can go before you have to regenerate. Depending upon the specific scenario, it's generally possible to transmit at a 50% lower cost per bit with this new fiber, depending upon the exact distance and the exact amplification method used. on to some specifics about this new G654E fiber itself. The first thing that we've done is reduce the attenuation. We've implemented a pure silica core for the transmission, and that's been able to drive attenuation to less than 0.17 dB per kilometer at the 1550 nanometer transmission wavelength. Another thing we've done with this fiber is it's got a new waveguide design that reduces microbending and macrobending loss. And as all the G654 series fibers do, it has a high cutoff wavelength, which tends to reduce macrobending and microbending loss. So it makes it relatively friendly to cable. And the final thing that we've done to this fiber is it's got a very large effective area to support the high power launch. The mode field diameter is 12.4 versus a typical of about a little bit less than 10 for a G652D fiber, and has a nominal effective area of 125 square microns. A lot of what this paper is focused on, or this presentation is focused on, is how does this fiber perform out in the field? This new fiber is a great product. It's a wonderful fiber, but as with kids' toys or IKEA furniture, some assembly is required. Our end customers don't use spools of fiber. They use cables out in the field. And in order to deliver value to the customer, we have to deliver on this low-loss performance as in the form that customers actually use the fiber out in the field, in cable. From talking to a lot of customers, we've determined that a loose tube cable design, outside plant loose tube, is ideal for these kinds of high-speed long-haul applications. As customers build city-to-city routes, often along highways or railroad right-of-ways, it's ideal to have a mix of different fibers in the cable. Some of the tubes contain the new G654E fiber as an express lane between those major nodes in the network. And the balance of the cable can be filled out with low-loss G652D fiber as a local lane between those major nodes and the intermediate nodes where the users are. So loose tube is especially nice for this because it's possible to, as you add customers and add services to this cable on the low-loss fiber, you can access a tube that has the low-loss G652D fiber without disturbing the G654E fiber in the express lane. So loose tube works quite nicely here. Because a lot of the cost involved in building a network is the actual installation and splicing, we've selected 100% dry, gel-free loose tube cable for this application. And that saves a lot of time out in the field when the installer opens the buffer tube to expose the fiber. No gel cleaning is required, and the fiber is ready to go for splicing and termination. We tested a number of cables, a 5-position 60-fiber dielectric loose tube cable, a 12-position 144-fiber cable, and a 24-fiber 288-fiber cable. I'm showing the data for just the 5-position cable here for brevity, but we got similar results with the 12 and the 24. On this slide, I'm showing the data at 1625 nanometers, which is the most sensitive wavelength that we regularly measure. This transmission on this fiber will generally be between about 1490 and 1610. So this is kind of an extreme case. We had better results at this at 1550, which is typical. But as you can see from the slide, our average added attenuation in the core mechanical GR20 tests was very, very low. Excellent performance. It's a very robust cable. Going on to the environmental test results, one thing that's critical for these applications, it's important to meet the well-understood, well-accepted industry standards, but these users are also very concerned in the absolute as-received attenuation because that's how they're designing their power budgets and their network. So we wanted to highlight the as-manufactured performance. Another thing that I'm doing here that we don't normally do in cable is I'm quoting the data to the third decimal place. With the G652D fiber, we normally only quote the first 2 decimal places, but for this kind of application, every thousandth of a dB per kilometer matters to the overall long-haul system. Cable attenuation, at 1550 was under .18. Cable attenuation at 1625 is all under .195. During temperature cycling, very stable attenuation. We saw very little added loss either at either extreme of minus 40 C or 70 C. So we've met the standards, but the next thing we wanted to look at is how is this actually going to perform out in the field? What will our customers see? What we did for our installation simulation testing, we have a facility at our plant in Georgia where we have duct and handholds and other things to simulate real field installations. We wanted to follow attenuation in the cable from the fiber draw to cabling to deployment. And in this case, we chose to do that in a 24-position, 288 fiber cable. The reason we chose this design is the bigger cable tends to be more sensitive to bending and coiling and that sort of thing. So that's the structure of what we used. And we got some very, very good results. Typically, what we expect to see in cable is that when we take the cable off the field and deploy it, we expect the attenuation to drop. In cable, we have to wind the cable under tension on a reel. The reel has a relatively small hub, so we can maximize the length of cable on that reel. And that may drive up attenuation. It typically drives up attenuation just due to the bending and the forces on the cable in that reel configuration. But that's not how customers use it. They take it off the reel. But we have to measure it on the reel before we can ship it out the door to the customer. As you can see in the slides, attenuation at 1550 was about the same between as manufactured fiber and the complete cable. It went up a little at 1625, which is the most sensitive wavelength. But then upon deployment at both 1550 and 1625, we did see the loss recover somewhat, at least the average loss. And it went up a little for the maximums, or the maximums were a little bit higher than as made in the fiber. But as you string together long pieces of cable, the one or two outlier relatively high fibers, and these are still pretty low, will be averaged out with the low fibers, and we expect to have a very good overall system loss. So as deployed, we were able to achieve average of well under .17 at 1550, and also under .17 at 1625, which we believe are excellent results. Another issue out in the field is how do you fusion splice this new fiber? It's got a bigger core than normal fiber. It's got a huge effective area of pure silica. So it doesn't quite splice exactly like the traditional G652D fiber. Another thing that is important is that if you are in a network where you're worried about every thousandth of a dB per kilometer, you need to have the splice loss be as absolutely low as possible. Because a bad splice eats into your power budget, and enough bad splices, you could eat up your power budget and face bit errors in your transmission. So our fusion splicing group looked at generic recommendations that would work on any machine that's out there. There's multiple manufacturers of splicers that are made. Our company offers a splicer, but we know others do as well, and we want a fiber that's going to be compatible with anybody's equipment. So we developed generic splicing recommendations independent of what machine is used and who made that machine. For splicing of this large effective area fiber to itself, we found that we got very good results using clad alignment splicing, standard arc power, and we increased the arc discharge duration to 2 times the standard length. For that, we got the results shown in the plot on the right. Average splice loss was 0.038 dB, and the standard deviation splice loss was 0.028. So very good results for this generic recipe that will work across any splicing machine. We also looked at splicing to the G652D fiber. It's not something we would necessarily recommend, but it happens. There you get relatively high splice loss because of the mismatch in mode field diameter, because the G654E is has such a larger mode field diameter than the G652D. and our average was at 0.17 dB at 1550. Those were the generic recommendations. The team also worked on some custom machine-specific recipes for the splicers our company offers, and what we found is that we could drive the average loss down a little bit lower. So if there is interest in deploying this kind of fiber, customers can be supported with custom recipes that will absolutely minimize the loss. The final piece of the puzzle is we've got a fiber that meets industry standards. It performs well in our simulated deployment. The customer is going to be able to splice it when they get it. But how does it do over a large sample size, over large-scale production? So we looked at the as-manufactured performance of this of an initial production campaign using this fiber. Our first campaign, we ran 260 kilometers of cable back-to-back. They were a light armor cable whose structure is shown in the lower right of the slide. Gel-free buffer tubes wrapped with corrugated steel armor and a jacket. The cable was a composite, 60 low-loss G652D fibers and 12 ultra-low-loss G654E fibers. During the course of making these 260 kilometers of cable, which took us scattered over a month of production, we used over 3 megameters of this fiber in that construction. Our initial results on as-cabled attenuation, these are the production statistics for those 3 megs of fiber. At 1550, our average loss going out the door on reel was 0.172 with a standard deviation of 0.002. And as noted above, we expect that to drop when the cables are taken off the reels and actually deployed. Also had very good results at 1625, 0.182 average with the same standard deviation seen at 1550. Another way to look at the data is compare the incoming fiber attenuation versus the cable attenuation going out the door to the customer. At 1550, we did see a average change in loss, an increase of 2,000 dB per kilometer. But at 1625, we actually saw the loss drop. We attribute that to the sensitivity of that wavelength and the effect of the fiber packaging on loss, but good performance there. So to summarize the presentation today, as it has been doing for years now, the growth in Internet protocol traffic on the public network will march on, especially driven by video, mobile, and cloud applications. And traffic between data centers is growing faster than the overall traffic. Because of that growth in traffic between remote data centers, there is demand for higher speed long-haul transmission. That creates a market need for this higher capacity long-haul fiber. This ultra-low loss ITU G654E fiber has twice the ungenerated reach of standard G652D fiber, which will reduce the overall cost per bit of transmission for service providers. We've cabled this G654E fiber in gel-free loose tube cables and qualified that to the Telcordia GR20 standard with fully compliant results. And as shown in our installation simulation and initial testing, we can cable it we can maintain the low loss of the fiber, both cabled and deployed in an installation simulation. You can splice this fiber to itself with average loss less than 0.04 at 1550, which is a critical aspect for minimizing overall loss in a network. And finally, we demonstrated that the low as-drawn fiber attenuation was maintained in cabling of 3 megameters of this fiber in production cable. Finally, I'd like to acknowledge my coworkers in the different parts of OFS who helped with this work. Peter Burrell, Vera Paulsdottir, Dave Masries, and Alan McCurdy from our fiber team, Rick Norris and Barry Ward on the cable team, and Tom Liang from our fusion splicing team. Several other colleagues within OFS helped with discussions of this work, testing of the cable, and analysis of our production data. Thank you very much to all of you for your attention, and I would be happy to answer any questions in the time that we have left.
Thank you, Pete. At this time, we will ask as many questions from the attendees as time permits, starting with this first question. While you discussed the effectiveness of low performance for long-haul applications, where is the most effective transition to copper infrastructure? Indoor or at the curb of the data center or campus?
It depends upon the specifics of the network. As far as we know, there's still a fair amount of copper used inside these hyperscale data centers for reaches of 2 to 5 meters. And then it just depends upon the end user, what you're trying to deliver to the end user. Certainly within the home, copper makes a lot of sense. Copper can make a lot of sense for an enterprise based on what data you're trying to deliver to the customer. It depends upon the specific application. I'm a fiber person. I've been a fiber person for almost 20 years, but there's always going to be a place for copper in the network.
Okay. Next question. Are there capacity limitations on the long-haul infrastructure or mostly in data centers? And is the cloud capacity the limitation?
What we as a company have been seeing and hearing is that there are constraints on both, but the cloud capacity is probably being added quicker than the long-haul capacity because it can be done fairly quickly. So it seems like the cloud providers are always building and always expanding, trying to stay ahead. But we do believe we're at a point where some of our traditional long-haul routes are exhausted. Long-haul looks like it's more of a choke point than the data centers and cloud providers themselves.
Okay. Will cabling infrastructure designs need to further change as we transition to mega data centers as the Internet of Things or smart communities expand in the future?
It's a good question. We've been thinking about that, and we think the biggest change may be around things like Internet of Things and 5G wireless, where you sort of have more ubiquitous connectivity and you have lots and lots of small nodes. And we're thinking that maybe the situation there is going to require an awful lot of cables with not so many fibers, different from what we've seen today, that, it will be sort of maybe like, typically in a fiber to the home deployment, 1 or 2 fibers is provided to each end user. Well, as we go to these other applications, you might have a mobile antenna that's served by 4 fibers, but an awful lot of them. So that's one thing that, or an awful lot of cables like that. And then for the data center market, do the cables change? Depends upon, to a certain extent, it depends upon the electronics. Because if you need more capacity, do you do it with fiber and electronics, or do you do it with more fiber? Both are options, and I would assume that the cloud providers will choose what's most economical for them.
Okay. Next question. Why not use G654.E fiber express lane for everything? At this point in the evolution of demand and bandwidth, why use any G652.D within the tube at all?
That's another good question, and I think it depends upon the specific business case. One of the issues that the fiber has a more complicated waveguide than the basic G652D. It is more expensive to produce because more goes into it. And then the electronics to take advantage of this fiber are more expensive than the standard electronics. So it's probably overkill for the shorter reach applications, and probably we believe from our analysis that using these composite cables that have a mix of long haul fiber and shorter haul G652D would minimize both the CapEx and OpEx for service providers. So it's really a business case. We think the composite is the best value for the end user.
Okay, thank you. Next question. How about the fiber's microbending at 1550 nm?
I have to look that up. We reported the 1625 because it's the more sensitive. Wavelength. So I'll have to. I don't have the number at the top of my head. Certainly, it will be lower than what we reported at 1625 in the presentation. I don't think I have that number at the top of my head. I guess we can ask the person who asked that question can follow up with me offline. I'm quickly checking to see if I have that at the tip. Don't have that number off the top of my head, and I can't lay my hands on it quickly, so I would encourage whoever. It's lower than the 1625, so I'd encourage whoever asked to follow up with me offline. I'll have to check with my colleagues in the fiber team.
Super, thank you. Next question. Is water blocking technology used in these gel-free cables to help protect the G654E fibers?
That's another good question. The gel-free cables have been on the market for a little over a decade now. We use them. I think it's useful to protect all fibers, regardless of what type they are. The benefit to the installer is the savings in installation time, but the water blocking materials are there to comply with the industry standards for water penetration. But they also help they also help protect the physical and mechanical integrity of the fiber, whether it's a G652D or a G654E. We actually did a paper at the IWCS about 16 years ago when we were first doing research on this topic. And what we found is that the water blocking materials, in this case it's a thread with superabsorbent polymer, they tend to control the humidity inside the cable, because if you get water diffusing in, it's going to get absorbed in the superabsorbent, which acts kind of like a desiccant. And that's a good thing, because it turns out that the optical glass, or any glass, is actually fairly sensitive to water. Water can degrade glass. So it does have a beneficial effect for the long-term life of the cable, in addition to preventing large distance water propagation in the case of cable damage.
Okay, thank you. Next question. It's a splicing question. What is optimum arc discharge duration? It
is 2 times the standard recommendation, and I don't know what the standard recommendation is off the top of my head. And that's sort of whatever your standard arc discharge for a G652D to G652D splice. We recommend 2 times that. And then for I think we recommend a significantly longer arc duration when splicing the G654E to G652D. So it's, I don't know what the baseline time is off the top of my head. It's on the order of 3 seconds, I think, but I don't know exactly.
Okay, thank you. Next question. What is the type of splicing machine in the trial?
The splicing machine in the trial was a Fitel S122. But we also did look at splicers from Sumitomo and Fujikura. Most of the work was done with the Fitel S122.
Okay. Next question. Do you observe any large unidirectional OTDR gainers at splice points, both to itself and to G652D fibers? If yes, what's the explanation?
With the G652D to this fiber, yes, you're going to see some pretty big losers and gainers. And the explanation is the difference in mode field diameter at 1550. This fiber is 12.4 micron mode field diameter. The G652D is a little bit under 10. So any light, when you butt circles that size up against each other, the light will, if you're going from the G654E into the G652D, any light that's outside of the spot of the 10 millimeter G652D accepting it is going to be lost. So that's going to show up as a big loser. Likewise, if you're going the other way, you'll see a big gainer. And then for splicing it to itself, with any fiber, you have the possibility of seeing losers and gainers just because we'd like to make every fiber with absolutely precisely the same mode field diameter, but there is, slight within spec variation in mode field diameter. And if you happen to, by circumstance, splice one fiber at the bottom of the mode field diameter distribution to one at the top of the mode field diameter distribution, you might see unidirectional losers and gainers. It is certainly our recommendation that end users do bidirectional testing to account for those losers and gainers, but sometimes that can be hard to do out in the field.
Okay. I see no more further questions, so at this point I would like to thank you, Pete, for presenting this very interesting and important topic today. Please note contact points being shown should you wish to contact Pete after today's event. Each of these IWCS webinar series presentation events are recorded and will be archived on the IWCS.org website. It normally takes up to 2 weeks for these to be posted. The IWCS webinar series will conduct presentation events on a monthly basis. Webinar events will take place on the third Friday of each month at 10:30 a.m. Eastern USA time. Our next scheduled webinar event will be on Friday, April 21st at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for the event a few weeks prior. Please feel free to share our announcements with your colleagues so that they can join in and register as well. For over 65 years, the IWCS International Cable and Connectivity Symposium has been the recognized leader showcasing new technologies in cable and connectivity products, processes, and applications. Our next annual international conference will take place on Sunday, October 8th through Wednesday, October 11th, 2017 at the Gaylord Palms in Orlando, Florida, USA. In addition, the inaugural regional UL and US IWCS China 2017 Cable and Connectivity Symposium will take place on Tuesday, April 25th through Thursday, April 27th, 2017 at the Marriott City Center in Shanghai, China. Please visit our website at iwcs.org for more event details. In just a moment, you will see a brief survey so that you can provide us your feedback and comments on today's event so that we can further improve this webinar series for you. Thank you for participating, and this concludes today's event.